Hello and welcome. This video is CCBYNC. Welcome to the next trig piece. We're going to deal with basic trigonometric functions. This is our most fundamental, and the three big ones are the sine, the cosine, and the tangent. And it's all based on a right triangle that we have here. Here's a typical right triangle where we have an angle capital A, and the opposite side is a lowercase a, same with the B and the C. Typically, C is the hypotenuse. And it's all, each of these three functions that we're going to talk about today are all based on a specific angle. So relative to angle B, the side over here is what we call the opposite side. So it's completely the opposite side versus this side here, which is what we term as the adjacent side. The hypotenuse is always the hypotenuse. Now, if I were to base things on angle A, then the opposite would be here, and the adjacent would be over here. But this is all relative to angle B. Sine of an angle is going to be the opposite side over the hypotenuse. And you'll see it written this way often as an abbreviation. So the sine relative to A is the opposite, that's A, over the hypotenuse, which is C, which you see here. Relative to B, like I did before, the opposite is side B over the hypotenuse, which is C. Cosine is the adjacent over the hypotenuse. And again, you'll see it abbreviated this way often. And you can see cosine relative to angle A is the adjacent, that's side B, over the hypotenuse, side C, B over C. Relative to angle B, so if I'm up here, the adjacent is right on this side, the adjacent A over the hypotenuse C. Tangent is the opposite over the adjacent. And so relative to angle A, the opposite is A, lowercase a, over the adjacent, which is B, so it's A over B. Now relative to angle B, when I'm up here, the opposite is B over the adjacent A. And you can see they're backwards. Now, someone came up a long time ago, way before my time, and came up with sort of a way to remember this. And you often pronounce this SOH CAH TOA, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. If that's a helpful way to remember that, then certainly do so. But you will need to know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is the opposite over the adjacent. There are three other trig functions that we're not going to deal with today, where they're the upside downs of each of those. We'll get to that in another lesson. All right, let's apply this. We have our triangle here. It says find the values of the three trigonometric functions of angle A. So here's the angle A. Everything's going to be based off of this angle up here. So if I want to do the sine of A, I use parentheses all the time. Some teachers don't. They just do sine of A like it's written up here. If you remember, sine is the opposite over the hypotenuse. And relative to angle A here, the opposite is 9 over the hypotenuse, which in this case is 15. We can, of course, reduce that. We also have cosine of A. If you remember, cosine is the adjacent over the hypotenuse relative to angle A. So here's angle A, here's the adjacent, it's 12, over the hypotenuse, which is 15. And once again, that reduces to 4 over 5. The tangent of A, again, is the opposite over the adjacent relative to angle A. So here's the opposite is 9 in this case over the adjacent, which is 12 in this case. There are our three trig functions based off of angle A. We'll do another example. So for example 2, First, they say find the hypotenuse. So in this case, we only have the two legs. But what I can use is the Pythagorean theorem, of course. I'll call this side h for hypotenuse. So h squared is 5 squared plus 12 squared. So 25 and 44 is 169. And if I take the square root of both sides, our hypotenuse is always positive. Square root of 169 is 13. So part A is finished. Part B says find the three trig functions based on angle x. So here's angle x. Sine of angle x is the opposite, which in this case the opposite is 12, over the hypotenuse, which we just got is 13. Cosine of x, here's x, is the adjacent, that's 5 over the hypotenuse, which is 13. The tangent of x relative to x is the opposite, which is 12, over the adjacent, which is 5. Part C says do the same thing relative to angle z. So now we're down here. And the sine of angle z is going to be the opposite, which is 5, over the hypotenuse, which is 13. Cosine of z, here's z, is the adjacent, that's 12 over the hypotenuse, which is 13. Now, you're probably going to start seeing some patterns here. The tangent of z, here's z, is the opposite, 5 over 12. And these are patterns. The sine of one is often the cosine of the other. That's what makes them co-sines, right? And the tangent and the upside down of tangent is called cotangent, actually. That's where that comes from. All right, we've got a few more examples. So consider an isosceles right triangle with legs of length 2. Find the sine, cosine, and tangent of both acute angles. So first thing we're going to do is draw. If you remember, an isosceles triangle is one where the two sides are the same that make up the right angle. And they tell us that this is a length of 2, which makes this also a length of 2. And to be clear, well, we'll use the Pythagorean theorem to come up with that. We could also recognize that this is going to be a 45, 45, 90 triangle and use our special right triangles to come up with the hypotenuse. So either way works. Either way, what we get for the hypotenuse is 2 root 2. And I'll work that out down here. So I'll call that h again for the hypotenuse. It's going to be the square root of 2 squared plus 2 squared, which is 4 plus 4 is 8, which is 2 root 2. So that's where our hypotenuse comes from. And I'm going to call this one A, this one B. Here's our two acute angles, both acute angles. And I call them A and B. So let's find the three trig functions for both of them. So we'll start with angle A. So sine of A, again, is the opposite. So here's A, opposite 2 over 2 root 2. The 2's reduce out, and we actually get root 2 over 2. Cosine of angle A, that's the adjacent 2 over the hypotenuse, 2 root 2, which you can see is going to be the same as the sine. which isn't surprising since we know that's a 45, 45, 90. And the tangent of A is the opposite 2 over the adjacent 2, or in this case, a 1. Now what I can do is now find sine, cosine, and tangent of angle B. So here's angle B. Remember, it's the opposite. That's 2 over the hypotenuse, which is 2 root 2, which once again is the same. Cosine of angle B is the adjacent over the hypotenuse. The tangent of angle B is the opposite over the adjacent. There we are. Example 4. Consider a 30, 60, 90-degree triangle with a hypotenuse of length 10. Let's go ahead and draw that again. And we're going to draw on our special right triangles. And I'll say this is the 30-degree. This is the 60-degree. Of course, this is the 90-degree. And we have a hypotenuse of length 10. If you remember your special right triangles, the side opposite the 30-degree angle is exactly going to be half the size of that. So that's going to be 5. The one opposite the 60 is going to be this one times root 3. So you may need to review your special right triangles with that. All right, so let's say, what is the sine of 30 degrees? That's the opposite over the hypotenuse, which in this case is 10, or 1/2. The cosine of 30 degrees, here's 30 degrees, is the adjacent, 5 root 3 over 10, which is root 3 over 2. The tangent of 30 degrees, here's 30 degrees, is the opposite over the adjacent, and if I rationalize that denominator, that looks like this, root 3 over 3. You have to see what your teacher says about that. Some teachers make you rationalize it, some don't. Let's now do the sine of 60 degrees. These are two acute angles. So here's 60. The opposite is 5 root over the hypotenuse, which is 10, or root 3 over 2. And once again, you'll note cosine of 30 degrees is the same as sine of 60 degrees. These patterns come up all over the place, all the time. Cosine of 60 degrees. The reason is because they're connected like that is because they're complementary angles. All right, here's 6 is the adjacent. Cosine is adjacent 5 over the hypotenuse, which is 10. 1/2. Again. Tangent 60 degrees. Here's 60 degrees is the opposite. 5 root 3 over the adjacent, which is 5, which turns out to just be root 3. One more to go. Consider the right triangle, ABC. If sine of A is 9 over 41, find the length of the third side. All right, so let's draw a nice big triangle here. And I will call this angle A. making this B, making this C. And if you remember, the sine is the opposite, so that's going to be the 9. Let's color that up a little bit. So it's the opposite, which is 9, over the hypotenuse, which in this case is 41. And you see the sine is the opposite over the hypotenuse. So what they're looking for is they want to know, what is this missing side, which I'll call x? Well, what I can use, and just to be clear, that is the opposite of a, that's the 9, and this is the hypotenuse. So let's use the Pythagorean theorem. Now, notice we're missing the length of a leg. So that's going to give me 9 squared plus x squared equals 41. And I don't happen to know what 41 squared off the top of my head is. 41 squared. 1681. Minus 51. 1600. And I believe that comes out to be 40 if I take the square root. Let's see. Square root of 1600 is 40. So what's the missing side in this case? It's x equals 40. Thanks.